Okay, we ended up talking about rotation, so let's talk some more about rotation. I may have not stated something clearly yesterday. I think I said it clearly, but or drew a nice picture, but I may not have written it clearly. Suppose you have a vector that you have already rotated to the xz plane, and if this is the vector we're talking about, and this would be the y-axis going into the board, but then you know to get it to the x-axis, I don't know if I call it plus angle, minus angle, but literally you have to rotate this by this much, correct? And suppose it is at a lower angle, you're rotating it by a negative direction. I said minus y-axis, I'm not sure if that's accurate. But you look at the vector and you just rotate. The point is, huh?
I'm sorry, it's just think like the rotation, if you were to take the positive y rotation and then make it a negative y-axis, it'd be the same.
Yeah, I'm not entirely sure I wrote down correctly, but you know from context what I mean. Just visually look. Okay. So one of the things we want to do is to make sure remember we defined rotation. It has to be linear, inner product has to be preserved, then Ex cross Ey dot Ez has to be 1. So if you want something to be linear, there's really only one way to go. Right? Rotation as a matrix. Right? If I wrote it as a matrix, I would do R11, R12, R13, R21, you can fill this up. So for example, what would this be?
That'd be R32.
R32, good. And then if you want to rotate, you know if you're rotating bases or the unit vectors or the vector itself, they transform exactly the same way. So suppose you have a vector vector v. If you want to look at it in some rotated coordinate, the ith component of that can be written as r, a summation symbol, r I j v j. Correct?
Is that complex conjugate V?
No. This is
Oh, sorry, V bar. It's V bar.
Yeah.
Yeah, I see. That's the rotating.
Components in the
rotated.
new frame. Yeah, rotated frame. This is in the one that you had before. Okay, so what I want is, if I took it, and now it's going to be tricky how to write this, so let me color code it. Because remember in my notes, vector V is a bold. Here it's not. So what if I have two vectors and I find its inner product in a bar frame, this confusion will go away pretty soon. It should be the same as the dot product in the non-rotated frame. When you rotate things, you're not changing the inner product. Is that clear? So how can that happen? Well, let's see. I want this to be a matrix. So I can write V bar dot W bar is equal to, tell me if this is correct, R I J V J R K L V W L. And I'm going to sum over
I
and
K.
J L, and what do I need? I equals Let me make sure I write it correctly, the way I wrote it in the
I
notes.
equals L.
IJK. So let me do it this way. IJL.
Yeah, okay.
Because I'm taking the dot product. This remains the same. In this over here, it would be nothing more than V bar I, W bar I, sum over. I'm going to be careless here. I like the vectors to be here. Correct?
And it's equal to that?
Yeah, that should be equal to I, J, L. This is from 1 to 3. All summations are from 1 to 3. Now, how do I make this matrix multiplication, guys?
It'll just be the.
How do you matrix multiply? Can I do this? I'm going to take this guy and then leave the rest alone. Is that considered matrix multiplication? Because so this one I just copied. These three I just copied. Right? This one I transposed it. But then I transposed it again. LIL became LI.
Over that first summation on the bottom row, is that a bar or just the vector?
The components of the vector in the bar coordinate.
Okay.
Yeah. So really what I mean by that is V bar 1, W bar 1. It's a dot product, right? V bar 2, W bar 2. V bar 3, W bar 3. And I want this to be nothing more than that's where I want to end up. This has to be the same for any choice of V and W. When does this happen? How can this combination for any choice of V and W become this? What happens if I multiply these two and I get the identity element? First of all, do you recognize this to be the matrix do you recognize this as matrix multiplication? You do. Good. Suppose what happens if I have R, T, L, I times R, I, J to be equal to delta Lj. What is delta Lj?
It's the Kronecker delta.
Kronecker delta. So is that the identity matrix? It's equal to 1 when I equals j. It's equal to 0 otherwise. Yeah? What happens if that's the case? Then this guy becomes what?
Just the exact same thing as.
Well, let's see. I, J, L. Then I'm going to write this as delta L, J, J, W, B, okay, J, L. Right? I has already been multiplied out. Right? We've done the sum over I. That's what matrix multiplication is. Isn't that equal to nothing more than
Just J.
You guys are awfully quiet, so I want you to ask questions.
Makes sense.
Everyone okay? So how will you get a matrix to be rotation matrix? I can then conclude that if R is a rotation matrix, then R transpose R should be what? We actually saw this in the
Yeah,
C case.
Should be the identity.
Should be the identity.
So I have a question.
Yeah.
We're assuming that R transpose Li times R.
Well, if we, yes and no. If we assume we get the right answer, if you say no, you pick your, suppose the 1-2 component is not 0. You pick this to have only the 1 component and this to have only the 2 component, nothing else. Then you will see that it doesn't work.
Okay.
If you want the 1-1 component to be identity, then you pick V to have only 1 component, X component, and W to have only the X component.
So that's self-proving? in that
Yes,
case?
yes.
Okay.
You just have to do it 9 times, case by case,
Gotcha.
right?
Yeah.
You can prove that the 1-1 component has to be identity, the 1-2 component has to be 0, and so on and so forth. Otherwise, it simply won't work out. Is everyone happy? Happy with the conclusion? Okay. So we've taken care of linearity. We have taken care of the fact that the dot product must be the same. If the dot product is the same, the magnitude is the same. If the magnitude is the same and the dot product is the same, the angle has to be the same. What's the only check that is remaining? By the way, in your notes, I've stated this, I think, as a theorem, and I call it theorem 2.2. What's the only condition? I want you guys to participate a little bit more. What's the only condition remaining? Tucker, it's your birthday question. What is left for me to check? What other property should R have for R to be rotational? I had previously promised that I would raise a glass of beer on your behalf because it's your birthday. But for me to do that, you have to give me the answer. It's conditional now.
He's really hoping you get the answer right.
Yes, I'm very thirsty, Tucker.
Wait, what do we have so far?
We have
Magnitude, angle.
We have magnitude, we have angle, we have linearity.
Oh, yes.
Distance?
What do you mean by distance?
Is it not like distance has to be preserved?
You have your notes from yesterday? I ended with 3-4 criteria.
Yeah, did we already say one?
But yes, yeah, I mean, if the dot product is preserved, then the length is preserved. Why is that? Because the length is what? Square root of a vector dotted with itself. But the dot product is the same, so the square root is the same. So length is taken care of. If length is taken care of, angle is taken care of. Because V dot W is length of V times length of W times the angle, cosine of the angle between them.
And we already said the linearity is,
Linearity, because it's a matrix, it's linear.
and it'd be preserve the relative orientation of vectors.
Correct. Good. Thank you, I can have a beer today. So Tucker, you're just enabling people by answering, by the way.
I'd rather answer than get trouble for not.
Good. So, you can see R must satisfy one property in terms of its determinant. So, determinant of R transpose times R, well, it better be the determinant of identity. What is the determinant of identity? If you take an identity matrix and you find its determinant, what is it?
Determinant of the identity should be 0, right? It's 1.
1.
Not 0.
The other 0.
Yeah.
Think about the cross product.
Yep. Now, if you recall is always dangerous. You might say, well, I haven't seen that before, so how do I recall? But you can look it up. Determinant of A times B is what?
B plus times B.
That's true. Doesn't seem like it should be, right? But it's true. Determinant is actually an amazing thing. There's another property.
Yeah.
So then we have, that means this implies determinant of R transpose times determinant of R equals 1. This implies determinant of R times determinant of R equals 1. This implies the determinant of R equals what? Give me the full answer.
1.
The full answer.
Determinant of the identity.
Let's see. Determinant of R would be equal to the square root of 1, which is equal to 1.
Huh. Determinant of R is a number. So let's say if I have a symbol A squared equals 1. What are my answers?
Plus or minus 1.
Plus or minus 1, correct.
Gotcha.
So we know this. Which one do we pick? Or do we pick both? So look at this. If I have E bar 1, E bar 2, E bar 3. And that's equal to R11, R12, R13. You fill it. R33, E1, E2. And these guys are vectors. We know that, of course, E1 cross E2 dot E3 has to be equal to 1. We also require that E bar 1 cross E bar 2 dot E bar 3 must equal to 1.
Have we said somewhere that cross product is also preserved? Because we know that the inner product is preserved. But
No, we haven't said the cross product is preserved. It's not preserved because it's a vector.
yeah.
So the cross product also changes direction.
But whenever you dot so E bar 1 cross E bar 2.
Yeah. Oh, right. So we talked about this. So if I take a basis, X, Y, Z, this is my orientation. But if I'm rigidly rotating, this is my X and this is my Y, and if I do X cross Y, what should I get? The new Z. The axis cannot all of a sudden
Okay.
flip back to the other
So
side.
if you dot that with E bar 3, no matter what,
Yeah.
it should always give
Yeah,
you
because they're rigidly rotating. When you do your right-hand rule, this might sound silly, but this is the proof. When you do your right-hand rule, you can do it this way, or you can rotate it and do it. Right? And that's the orientation. You will show that this is nothing more than determinant of R. Well, write it out. Right, instead of E1, you write it out. this much, and you know E1 dot E2 is 1, sorry, E1 dot E1 is 1, E1 dot E2 is 0, and so on and so forth. When you do all that math, you will get this to be precisely that. Therefore, I can conclude that while I may actually have two choices, the rotation matrix itself must be such that the determinant of R is equal to 1. Any object that transforms according to this rule is a rotation matrix. And clearly, our construction can be written the other way, just everything is equal to one thing, so you can write the proof backwards. If it is this, it is a rotation matrix. Conversely, if it's a rotation matrix, it is precisely this. Yeah? So what I'm saying is, if I take any matrix whose transpose is the inverse of the matrix, and the determinant is identity, isn't that what this is saying, by the way, guys? The transpose is the inverse, because it's identity. So if you find any matrix whose transpose is the inverse, and such that the matrix has determinant 1, that matrix is a rotation matrix. And any observer that changes according to that will clearly measure the speed of light to be c. No, you've only rotated. Yep. So definition, set of all 3 by 3 matrices satisfied is called the rotation group. We have to work a little hard to call it the rotation group, but for now we can call it anything we want. And is denoted by the symbol uppercase S, uppercase O, 3.
Do you mean that R transpose R is equal to 1, or?
Identity. Very good.
Does it only work the three-dimensional
I
matrix?
think it's right.
Yeah. There's probably like different rules for other dimensions.
Yeah. I haven't,
I mean,
I say this from memory.
not greater dimensions, but like lesser dimensions. 'Cause
No, even, you can define rotation in higher dimension.
you just can't understand. You can't visualize it.
Yeah, but once you work with the definitions, you'll gain some sort of an intuition. Let me explain this term. It's one of the most important groups there is in physics. The word S stands for special. It means determinant is 1. O stands for orthogonal. It means this condition is true. And slowly, it's not important now. We'll see some more properties, I think. There's lots you can study about SO3. But I call this what? A rotation what?
Matrix.
No, I didn't call it a rotation matrix.
Oh, yeah.
Group. So it's a group is a bag of list of things. It has all matrices that satisfy these two conditions. But for it to be group, it has to satisfy additional properties. What is a group in mathematics?
It will be operated upon. Right?
There must be a group operation, Yeah? There must be an inverse. So let me clarify all the properties of what it means for it to be proved, because it's important to us. So this is problem 2.3, but let me state it. Problem 2.3. So which means you have to show that, you'll find the complete sentence in the notes, but I'm just giving you the basic. Show that identity matrix is a rotation. A group must have an identity element. That's trivially true, right? The transpose of identity is identity. Identity times identity is 1. Determinant of identity is 1. You're not really rotating, but it's the identity element. You must have that if R1 and R2 are rotations, then so is R1 multiplied by R2. So if the group operation here is matrix multiplication. So when you, like numbers, when you multiply numbers, you cannot all of a sudden get something else. You cannot get, a column. Number times number is a number. So matrix times matrix better be a matrix. Well, it's a matrix, but a rotation matrix times a rotation matrix should be a rotation matrix. This is a problem, so you have to work on it. Because all you have to show is this product satisfies these rules. It's easy to do. You can look up all the matrix properties of matrices. And, sorry?
I would say so it just has to be recursive and R has to refer to itself.
Correct. If you take two elements of R, or two elements of SO3, and you multiply it, you get another element in SO3. Yeah? And then the last one, if R is a rotation, so is R inverse. How do you know R inverse exists?
Because
this is not a course in linear algebra, but when you take linear algebra, you will know that any matrix whose determinant is non-zero has an inverse. But guess what?
determinant is not 0.
Our matrices do not have a determinant zero. So inverse exists. So you have to show that the inverse matrix satisfies this. This is not difficult to show. Inverse of R is the transpose of R.
Do you want us, in this case, to calculate the inverse using inverse calculation? Like
No.
inverse matrix calculation?
We know it's transpose.
Okay, so we just know that it's already transposed.
Yeah. So if R is a rotation, then
Transpose will be 0. The transpose should just be the opposite rotation, right?
no, right, it's the opposite rotation. And so when I say transpose, what do I mean? So normally I write 1, 1, R1, 2, R1, 3. What would the transpose look like?
You flip along the diagonal, so it'll be.
Yeah, you flip along. So
1,
this
1,
will remain the
4,
same.
It'll be
This
2, 1,
2, 1.
3, 1.
Yeah, good.
Where's your 3?
Did we do?
I didn't remember that it was worth it.
I remember things by and stuff like that.
Yeah, I mean, yeah, we've done this one first. Yeah, transposing is not an issue.
Good. I'm in no rush. How are we doing?
Pretty good.
No, you feeling good?
Yeah, I think that was probably my greatest shoulder.
Veronica, are we happy?
Sure.
Sure is not so.
Happy is subjective, I think.
In this class, you should be happy.
Sure.
Good. Nice. Okay, so, all right, now what I'm going to do is just to list the bag of all inertial observers. You should be somewhat wondering this question, why are you obsessed with inertial observers? crying out loud, we've been doing physics for some time now. We haven't really spent time on who can do physics. That's what inertial observers are, right? Inertial observers are observers for whom the laws of physics remain true, remain valid. So you should be at some level asking, why are we obsessed with who can do physics? Let's just do it already, right? But it is a fundamental question. All types of particles in the universe are determined by the properties of who can do physics. That's it. Equations of physics should have an appearance that is governed by the rule of who can do physics. So this is section 2.2, classes of inertial observers. Just going to label them. So time translated observer. So this observer has t bar equals t plus what symbol did I use? Plus some t0, some constant. Time has been translated. For example, if t is Eastern Standard Time and t bar is Central Standard Time, t0 is 1 hour. X bar equals x, y bar equals y, z bar equals z. Then delta x bar over, see that, delta x vector bar in the new frame over delta t bar equals c implies what?
It should also be constant,
Why?
because c remains constant no matter what frame.
No. Well, we don't know. Is it true here? Well, I know this is equal to that because x, y, and z are not changing. But t is changing, so why is this equal to that?
Because of time dilation?
No, not complicated. There's no time dilation here. There's no relative motion. You know, you and somebody in Atlanta sitting in a classroom, there's no time dilation.
Oh, because the time, there is, technically, even though the times are different, they change the same amount.
Correct. Because,
They might have a different initial value and they'll have a different final value, but
Correct.
their change is the same.
if 1 hour is gone for you,
1 hour is also gone for Central Standard, or for
Eastern Standard Time. So delta x is the same, delta t is the same, so their ratios have to be the same. This is, of course, the magnitude of the vector, right? So this is where delta x locates the point of, initial point of a photon and some final point that you've decided to measure. Okay, so what does that mean? These guys are
They're Yeah.
inertial frames.
they're
So-
on the same inertial frame.
Correct. I mean, not same, but I mean, they're both, if one is an inertial frame, so is the other. Very clearly, what about, I'm just going to state it, space translate. What does that mean? These are not standard names, I'm just using them to list it out correctly. What would this mean? It would mean this is equal to x plus some vector, what did I choose to call it? Some vector.
Okay.
I don't really need to elaborate this because what's going to happen? Delta x bar is the same as delta. Is that true, Gracie?
Yes.
Okay, why? Good answer.
It's like the same thing with the what happened with the timer.
Yeah. But what happened with time?
The change is still the same.
Change is still the same. Yeah, it's a constant.
Starting and
Yeah.
finishing is.
Yeah. Everyone okay with that? What do you think my next class is going to be? We spent a lot of time on it just recently.
Rotated?
Rotated, very good. Rotated observer. Do I need to elaborate? If you rotate, will your magnitude of the length change? The magnitude of the distance change? No, it's in my notes, you can read the words. Will delta t change with a rotation? No. What's the last class of observer we need to tack on? There's no way to phrase this properly. Lorentz transform observer.
So now the change in space and time will change.
No!
But C still remains the same.
But Steve, we spent a whole lot of time on that. Correct? These are the four classes of objects that preserve the speed of light. So we will call these objects an inertial observer if they're related by these operations. Now remember, this is again a bag of operations. You can first rotate a basis, then you can time translate, then you can Lorentz transform, then you can space translate. So at each point, each observer continues to be inertial. Yes, Kate.
So are all observers inertial from their own frame?
Yes, all of these observers. Yeah, you strap a jetpack on, you're no longer inertial. Once you turn it. Yeah? So, I mean, the whole point of rotating. Everyone good? Okay. Not so fun stuff. I may have mentioned Minkowski spacing, did I?
Not yet.
We'll talk more and more about this. So, the word space and time, there's no gap between them. They're, in some sense, one and the same. And you know, through Lorentz transformation, one person's time can get into a little other person's space. Watch for that in real life. So, because of that, I'm no longer going to do this X, Y, Z and a clock in my hand. Simply doesn't work. Because X and T can run into each other. You Lorentz transform in the Y direction, Y and T can run into each other. If you Lorentz transform in a direction which has X, Y, and Z component, X, Y, and Z and T can run into each other. So any event, any point in this Minkowski spacetime will be a collection of four quantities. And the quantities, four tuple, as we'd say. Four items. And you can see why I put that. Okay? And this will be collectively written as vector x, not vector, the point x mu. I will no longer use I, but I will, if I'm referring to space, the indices would be I. And I goes from 1, 2, and 3, the x, y, and z component. I will use mu, nu, lambda, Greek to denote space-time indices. Sometimes I use A, B, and C. This is usually done. But this I, J, K, L, M, N is usually reserved for space indices. When in doubt, ask me. I'll try not to violate those rules. So this guy, this is x1, x2, this is x3. So when mu equals 1, it's the x coordinate. When mu equals 2, it's the y coordinate. When mu equals 3, it's a z coordinate. This is mu equals 0. Yeah? So now, any inertial transformation is a combination of all the transformations that are allowed, can be written in this form. I want to explain a few things. Obviously, it's a matrix, and I want to explain up and down. And I want to explain something that we will be using for a long time yet.
What's that mark right there? After the lambda.
Lambda, mu, nu,
Oh, it's new.
x nu, a mu. There are a few things to note. And this will be a good point to stop. But let me mention the Einstein summation convention. Before Einstein, I think, I'm not very good with history, and people were writing all these equations. Gosh, they had I, J, K, and if you start doing more and more stuff, you might have, so let's go Greek, nu, lambda, sigma, it just gets ugly. So Einstein said there's a way to fix all of this. Just avoid clutter. If you see a repeated index, where one is up and the other is down, it implies summation. So, let me be clear, and I'm going to stop here. We'll pick up here next time. So this means in particular, for a fixed, let's say, lambda 1 nu, x nu, this will be lambda 1, 0, x 0, plus lambda 2, 0, lambda 1, 1, x 1, plus lambda 1, 2, x 2. Seems like very confusing and unnecessary, but then it'll be like the movie Matrix. You won't see summation symbols anymore. Anytime you see summation symbols, it'll just irk you. You'll just look past them.
So is the first mu a subscript on a lambda? Is that what that is?
Oh, correct. This is a matrix.
I see. Okay, I thought it was modifying the x. I was like,
Sorry.
What?
This is a matrix lambda
gotcha. Okay.
that matrix has two components.
Yeah.
Now I'll talk about y up and y down. Yeah? But the mute component of the new vector is equal to this formula. Let's unpack the formula. But today, that's a good question, Veronica, I should have clarified. Is the summation convention clear? Yeah. I mean, otherwise, we'd have to do this or that. But Einstein just said, you just look at this and see this. In the beginning, you're looking at this and inserting this in your mind. Give me 2 weeks, if someone writes this, you only see this. This just becomes unnecessary. Yeah? Okay.